A solar farm on land is a quiet place. Out on the water, it is a constant physical battle. The panels are locked to industrial pontoons, and every wave exerts hundreds of pounds of kinetic force directly into the structure. Ground-mounted solar systems rest firmly in the soil. They deal entirely with static loads, dead weight and occasional wind, making them rigid and predictable. A floating array, however, is in perpetual motion. It faces continuous wave-induced twisting, wind shear across the open water, and mooring lines that must tighten and slacken with drastic seasonal changes in water levels. Sending technicians out on boats to perform manual inspections across acres of bobbing hardware is slow, dangerous, and expensive. The environment is actively trying to tear the power plant apart, and human operators simply cannot track every point of mechanical stress. Physical engineering alone cannot ensure the plant's survival. To keep these panels generating power, the array requires an active digital nervous system that reacts to the aquatic environment in real time. To monitor an installation of this scale, operators deploy dense networks of sensors across the physical structure, tracking thousands of distinct data points simultaneously. These sensors pulse telemetry at rates of up to 10 Hz, 10 times every second. Standard supervisory control systems are quickly overwhelmed by this constant, high-resolution stream of information. The network tracks structural pontoon strain, tension imbalances across mooring lines, raw electrical output per module, and shifting meteorological conditions. Managing that volume of raw data requires artificial intelligence to ingest the noise, find the physical patterns, and issue precise operational commands. The AI acts as the plant's brain, transforming an overwhelming flood of sensor data into an immediate, actionable survival strategy for the entire array. Rather than waiting for a component to snap or short-circuit, the system mounts an active defense. Autonomous drones launch over the array to run preemptive inspections. This flowchart details the AI architecture. Drones process thermal feeds through a CNN-LSTM network. The CNN extracts spatial features to map physical defects, while the LSTM analyzes temporal trends to spot anomalies a single photograph would miss. This confusion matrix shows the system's performance. By analyzing the data in real time, the network successfully identifies microcracks, localized soiling, and electrical hotspots with 92.3% accuracy. By pinpointing exact stress points before they escalate into mechanical failures, the system transitions plant management away from reactive, water-based emergency repairs to highly targeted preemptive maintenance. All the telemetry collected from the drones and surface sensors is fed upward into the cloud to construct a high-fidelity digital twin of the facility. Inside this virtual environment, the AI runs continuous simulations, modeling the precise heave, surge, pitch, and mooring forces the plant will experience based on incoming weather forecasts. It calculates invisible structural fatigue and identifies risks, like insulation degradation inside submerged high-tension cables, hours or days before a storm actually hits. The system also protects the plant's financial output. If the forecast predicts severe weather that will force hardware offline, the AI optimizes smart battery management to dispatch stored energy to the grid at peak rates before the shutdown. The digital twin gives the physical plant the ability to practice surviving storms in the cloud before facing actual wind and waves in reality. Once a degraded panel is identified, the system deploys ground-based cleaning and maintenance robots directly to the affected module. The aerial drones transmit coordinates and fault data straight to these robots. By utilizing edge AI processing on the machines themselves, they bypass the latency of communicating back and forth with the central cloud. This flowchart illustrates the robot's deep queue network decision-making architecture. The agent evaluates dust density and energy to select low, moderate, or intensive cleaning. Through a reward-based feedback loop, it learns to balance mechanical wear, battery life, and water conservation. This localized robotic coordination reduces overall water and energy consumption by over 34%, while restoring up to 31.2% of energy output on heavily soiled panels. At a macro scale, these intelligent arrays integrate seamlessly into existing power infrastructure. Many are installed directly on reservoirs alongside hydroelectric dams. By sharing transmission lines, the AI creates a virtual power plant. It load balances the intermittent solar generation with the steady output of the dam, guaranteeing a stable baseline of electricity. In parts of Asia, operators practice agrovoltaics on the water. The AI dynamically manages panel orientation to provide optimized shade for fish ponds below, reducing water evaporation and increasing aquaculture yields. Excess energy from the floating arrays can also be routed into nearby electrolysis facilities, converting the water directly into floating green hydrogen for long-term energy storage. Through precise data management, the floating farm evolves from an isolated power generator into a versatile load-balancing hub that supports the wider global grid. This chart shows the economic race to control these technologies. Annual patent filings for the physical floating pontoons and anchoring structures climbed steadily before peaking in 2021. The basic hardware is now well established. The new frontier of investment is digital. The AI architectures analyzing data streams make these massive ecosystems bankable. Current patent data reveals vast growth potential in two distinct areas: grid integration and energy dispatch, and the environmental management of aquaculture. By wrapping unstable aquatic environments in predictive digital networks, engineers have turned chaotic natural forces into self-monitoring, self-healing, and profitable power plants. Artificial intelligence provides the precise control needed to harness the immense surface area of our lakes and oceans, generating clean electricity without sacrificing a single acre of usable land.